Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question.
So yeah, today's question is twice greater. So in this question, we're given an array B of length m and it is called good if 2 times B of I is less than B of I plus 1 for all I in between 1 and 2. So for example, 1, 3 is good because 2 times 1 is less than 3. But 1, 2 and 1, 2, 3 are not good because 2 times 1 is not less than 2 and similarly 1, 2, 3 is also not valid. Also, let's say if this is the array, then this is valid because 1 is like 2 times 1 is less than 3. 6 is less than 7. 2 times 7, that is 14, is less than 15. So it is a valid array. But this is not a valid array because 2 times 9, that is 18, is not less than 15. Now we are given a sorted array B and we define f of B to be the longest length or length of the longest good subsequence of the array B. So for example, if the array B is 1, 2, 3, then f of B is equal to 2 because we can choose the subsequence 1, 3 from it, which is a good array. Right? Or for example, if this is the array, then f of A would be equal to 4 because we can choose all the 4 elements in a subsequence and it would be a good array. But if this is the array, then f of this array is going to be equal to 3 because we can choose these 3 elements and 1, 4, 9 will be a good array. Now we're given a sorted array A of length n and we need to find the sum of f of c for all the c which are non-empty subsequences of it. So for example, if this is our array A, then we can calculate all the 2 raised to the power n minus 1 subsequences of this array A, which would be like 1, 3, 1, 3, 1, 7, 1, 3, 7, and so on. And it would be a total of 15 such subsequences. And we need to calculate f of 1 plus this f of 3 plus f of this 1, 3, f of 1, 7, f of 1, 3, 7, and so on for all the 15 subsequences. And we need to print the sum of all of those f of c's. Now the answer can be very large, so we need to print it modulo this number. So we'll understand it better by seeing the test inputs, sample test inputs. But for now, let us see the constraints. And the constraints were given that the number of test cases will be in between 1 and 10 is to the power 4. N will be in between 2 and 2 into 10 is to the power 5. A of I will be in between 1 and 1 billion. And the array A will be sorted. And the sum of N over all the test cases will never exceed 2 into 10 is to the power 5. Now let us see the first sample input. So in the first input, we are given N as 3 and the array is 1, 2, 3. Now let us create all the possible 2 raised to the power n minus 1 subsequences of this. So we'll have 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. Now let us calculate f of each of these. Now f of 1 would be equal to 1 because there is one element. F of 2 would be also 1. F of 3 would be 1. F of 1, 2 would be 1 because we can choose either this one or this 2. Right? F of 1, 3 would be equal to 2 because in our subsequence we can choose this one and then this 3. F of 2, 3 would be 1. F of 1, 2, 3 would be 2. So the total sum of them would be 9. Right? Now let us see the second input. So there we have 4 and we have 1, 1, 1, 1. Now f of 1, 1, 1, 1 is nothing but 1, right? So in every subsequence that we choose, f of that subsequence of this array would be equal to 1, right? So the answer for this particular case would be nothing but the number of subsequences, which in this case is nothing but 2 raised to the power n minus 1, which is 15, which is the answer, right? So these were pretty much the sample inputs. Now let us move to the solution. So first of all, let us see how we can calculate the maximum score of f of b given some array. Right? So if let's say this is the array b, then what would be the value of f of b? Or what would be the length of the longest subsequence that we can choose, which is good. So in this case, we can choose 1, 3, 5, and 100, or we can also choose 1, 3. Uh, yeah, 1, 3, 5, and 100 is the most optimal one. We can also choose this 1, 3, 5, and 100, which would also give us a f of b as 4. And f of, like 4 is the maximum length of subsequence that we can choose, which would be good. So how can we like greedily pick up the best subsequence? So like optimally, like you can think of it as we can always choose the first element and then we'll choose the element which is just bigger than 2 times this first element. So we'll choose 3. Then the next element which we'll choose would be the smallest element which is just bigger than 6, which is 7. And then we'll choose the smallest element, which is just bigger than 14, which would be 100. Right. And why would this be the most optimal way of choosing? Because let us say by contradiction, instead of this 3, we choose this 5. So this, if we are choosing this 5, then it is just reducing the possibilities of choosing the next element further, right? So it's best to choose the smallest elements at every point, right? And because the array is sorted, this would easily work, right? So like optimal, it is best to choose the next smallest element, which is just bigger than 2 into a of n. Right, and that would give us the maximum length of the subsequence, which satisfies the good array property. Right. Now, how can we solve this question? So, in these kind of questions where we need to calculate the sum across all the subsequences of a, is usually either some kind of combinatorics or DP or a mixture of both. So, let us try to think of this in terms of DP. So, we'll define DP of I as the maximum score we can get starting our subsequence from index I. Right. So, and the index I is included. So, for example, if this is our array A and this is our index I, so we define R. Okay, let's remove this once. Yeah. So, let us say we're trying to calculate the answer for this index I. Right. Now, there can be multiple possibilities, right? So, what if I is the last element that is counted in our score? What do I mean by score? That is counted in this f of b, right? So, if I is the last element that is counted in the score, that means I'm not choosing anything after this, right? It's just like the first element I'm starting from, and this is the last element that is counted in the score. So this can come after this I, right? So like if my first element is one, then there is one, then there's one, then it is valid, right? Because it is starting with this one, and it is like this one is also like the last element that is counted inside our f of b, right? But if I like include f1, 3, then my f of b would be of length, right? So this 3 would also be included, right? So for these number of elements, right? So first of all, let us define R to be the first element after I, which can be counted in our score, right? So which would be nothing but like the element which is just bigger than 2 times A of I inside our array, right? So R is the smallest such element, right? So for these two elements, they won't be counted in the score, but we have the option to include them or not include them, right? So if I is the last element that is being counted in our score, so there is I, then I can have these two elements or in any subsequence, right? Like I can have any subsequence of these two elements. And how many such subsequences can we have? It would be 2 raised to the power r minus I minus 1, right? Because r is the next element which would be counted in our score if I include it after the element I. So how many elements do I have which are optional? Those would be these many number of elements, right? So if I is the last element that is counted in the score, I can simply add 2 raised to the power r minus I minus 1. Now what if r is the next element that is included in our subsequence, right? So I chose I have an option to choose anything or not choose anything from these. And r is the next element I'm choosing, right? So what would be the answer in that case? So in that case, the answer would be I have 2 raised to the power r minus I minus 1 options to choose or not choose anything from these, right? Into dp of r will give me, so yeah, dp of r will give me like the sum of scores of all subsequences starting from the index r. Right, so if I'm starting from index r, so dp of r will give me the sum of scores of all the subsequences which start from the index r, right? And I can add or not add any of these, so we'll be multiplying them with it. And this would be added in all the subsequences, right? So this would be added in the scores of all the subsequences starting from dp of r, right? So let's say we had something like 3, 5, 7, or something like that, right? So this would have given us a score of 3 and 7, which is 2. Now this 1 is also getting added, so I should be adding a plus 1 because this 1 is also getting, and this 1 would be added in how many such subsequences? It would be 2 raised to the power n minus 1 minus r, right? That is, for all these elements, I have an option to include them or not include them, right? After the syntax 3. So if I'm starting with 3, then how many subsequences would exist? 2 raised to the power n minus 1 minus r. And in all those subsequences, I can add this, like I'm adding this element, right? So if r is the next element, then what would be the count of my and dp of I, like how much would it contribute? So if I'm like adding this 1 after all the subsequences of this starting from R, so that would be 2 raised to the power R minus I minus 1 into dp of R plus 2 raised to the power n minus 1 minus R, right? Now what if R plus 1 is the next element? Then in that case, I would be adding like again for R minus I minus 1. These are like optional. I can have them or not have them. So that into dp of R plus 1 plus 2 times n minus 1 minus R plus 1. And similarly for any j, we can say that it would be 2 raised to the power R minus I minus 1 into dp of j plus 2 raised to the power n minus 1 minus j. And because the array is sorted, it would be valid for all the j greater than or equal to R. Now, how can we define dp of I? It would be nothing but 2 raised to the power R minus I minus 1. That is, this I is the last element included in the score, or the next element that is included in the score is some element R. So for that, we'll be adding this thing into this for all the elements from R to N. Now, this thing can be easily implemented in n square log n time, right? Because in log n time, we can calculate the element R, and in n square time, we can just easily compute this. But how can we optimize? So can we simply store like the summation of this as a suffix, right? Because this thing is a constant, this can come out and we can store like this much part in this suffix. So what would we basically be doing? So if it is stored in some suffix, then this thing would be simply simplified to this. So 2 raised to the power R minus I minus 1 plus this thing which came out into this thing is stored inside the suffix of R, right? And how would suffix of I be defined? It would be nothing but suffix of I plus 1 plus dp of I plus 2 raised to the power n minus I minus 1. In this way, I can easily compute the suffix of I. And now this can be easily implemented in n log n time. Why? Because I can calculate this R in log n time. And I can like iterate over all the elements once. So the overall time would be n log. Right. And this pretty much solves our problem. So now let us see the code in C++ and Python. So this is the solution in C++. So we'll begin by taking in the input of the number of test cases. For each test case, we'll call this function solve. Now in the function, we'll begin by taking in the input of n and the array. We'll sort the array. Now this is a redundant step. It's not really necessary because the given array is already sorted. We'll store the powers of true inside this vector. We'll calculate our dp and suffix. So we have defined our dp array and the suffix array with 0 initially. We have defined our answer with 0. The answer would be nothing but the summation across all the dp of I. Right, so the answer would be nothing but answer plus dp of I for all the values of I. We'll be running a loop from n minus 1 to 0. Let us define R to be the upper bound of 2 times j of I. Our dp of I would be nothing but 2 raised to the power R minus I minus 1 into 1 plus suffix of R that we discussed. Suffix of I is also nothing but suffix of I plus 1 plus dp of I plus 2 raised to the power n minus 1 minus I. And the answer will be nothing but the summation across all dp of I, and we'll be simply printing an answer at the end. And that's pretty much the whole solution. The time complexity is n log n because of this upper bound. And yeah, that's it for the code in C++. Now let us see the code in Python. So we'll run this loop for every test case. So for every test case, we'll be taking an input of n and the array. We'll be sorting the array, which is again not necessary because the given input is already sorted. We'll pre-compute the powers of 2. So we'll store all the powers of 2 from 0 to n plus 0 to n inside this list. We'll be defining our dp and suffix list. We'll be defining our answer with 0. We'll be running a loop from n minus 1 to 0, and we'll calculate our R, which would be the element just bigger than 2 times a of I. So this bisector is equivalent to upper bound in C++, which will give us the element which is just bigger than 2 into a of I in the array A. Now dp of I would be 2 raised to the power R minus I minus 1 into 1 plus suffix of R as we discussed. Suffix of I is nothing but suffix of I plus 1 plus dp of I plus 2 raised to the power n minus I minus 1. And the answer would be nothing but the summation of dp of I across all GVs. And in the end, we'll simply print an answer. Now the time complexity is n log n because this is log n and I'm running it n number of times. So it overall becomes n log n. And that's pretty much the whole solution. I hope you liked it. Thank you for watching. Bye bye.